Chapter 17. Engineering Properties of Rocks. Introduction. From civil engineering point of view, rocks are used for various purposes, that is, as site rocks for laying stable foundation, as building stones for walls, columns, lintels, and arches, as common aggregate, as roofing material, as flooring materials, as polished stones for framework, as paving separation of roads for making statues, as road metal, as railway ballast, as construction stones for bridges, piers, abutments, retaining walls, lighthouses, dams, for tunneling, and so on. A number of IS Indian standard codes are available to determine different engineering properties for rocks, such as crushing strength, shearing strength, density, toughness, resistance to abrasion, and durability by standard methods in the laboratory. Rock mechanics is the name given to the study of behavior of rocks in situ and in laboratory under loads or conditions imposed upon them naturally or artificially, statically or dynamically, and in all possible combinations or situations. The engineering properties can be logically studied under three heads. First, as relevant to the roads utilized as sites for construction purposes. Second, as relevant to roads utilized as materials of construction, that is, as building stones. And third, as relevant to roads used as aggregate, that is, small broken pieces of concrete or road materials. Different engineering property tests for rocks. Important engineering purposes to be tested or required for rocks. Different engineering property tests for rocks. Important engineering properties to be tested or required for rocks. Used as sites for foundation purposes, etc. Used as building stone or stone for construction. Used as aggregate. Then further used as after that used as sites for foundation purposes, etc. Further divided into laboratory tests and field tests. Laboratory tests are further divided into uniaxial compressive strength, tensile strength, shear strength, modulus of elasticity, triaxial test. Field test further classified into jack test, shear test, seismic test. Used as building stone or stone for construction, test further divided into crushing strength, transfer strength, porosity, density, abrasive resistance, frost and fire resistance, durability, appearance. Used as aggregate, divided into hardness test, toughness impact test, binding properties. Used as aggregate, further divided into hardness test, toughness impact test, binding properties, crushing strength, hydrophobic properties, cracking of concrete. Used as building stone for construction, further divided into crushing strength, transfer strength, porosity, density, abrasive resistance, frost and fire resistance, durability, appearance. Test for rocks used as foundation sites of construction. Sites with competent rocks are much more stable foundation of all important civil engineering construction. Rock foundations are always desirable because they offer a number of advantages compared with soil foundations. Field test. The determination of rock properties of a rock in nature undisturbed setup is more desirable than the determination in laboratory. The condensation and shear tests are of this kind. Jack test. This test is meant to find out the in situ deformation characteristics of site rocks. To conduct this test, a suitable trench is excavated and a hydraulic jack is made to rest on one side of the excavation or on the base plate or on concrete platform cast in situ. Jack test. This test is meant to find out in situ deformation characteristics of site rocks. To conduct this test, a suitable trench is excavated and a hydraulic jack is made to rest on one side of excavation or on the base plate or on the concrete platform cast in situ. After firmly adjusting the jack in this manner, a load is applied through the jack on the rock. This manner, jack. This is jack. This is port. This is plate. This is wall or trench or tunnel. After firmly, this is test galley or tunnel. This is side jack. This is rope pillar. This is vertical jack. This is test galley or tunnel. This is wall of a trench or tunnel. This is jack test. This is shear test. This is shear test. After firmly adjusting the jack in this manner, a load is applied to the jack on the rock. After firmly adjusting the jack in this manner, a load is applied to the jack on the rock. Shear test. The shear strength of a rock is also found out by applying the jack test in a modified form. A series of small pillars or rocks are first exposed within the test galley. Seismic test. This is a test of an appropriate nature. In this test, an artificial explosion is made at a particular plate and the shock waves, P and S waves, that is elastic waves generated there, move in different directions. When these velocities are utilized to study the deformation characteristics of rocks, the velocities of P and S waves are related to the modulus of velocity E and position ratio M as follows. Vp is equal to E into 1 minus M over rho into 1 plus M into 1 minus 2M, where Vp is the velocity of P wave, rho is equal to density of the medium. Laboratory test. Here is cylindrical core samples of representative rocks. Uniaxial compressive strength, tensile strength, and shear strength are defined in the laboratory. Uniaxial compressive strength. These tests are carried out on cylindrical specimens with a length diameter ratio of 2. The results are then reduced to length diameter ratio of 1 by using the formula C naught is equal to Cs into 0.8 plus 0.2 by L by D, where C naught is the observed compressive strength using cylinder of different diameter, L is the length of cylinder, and Cs is the standard uniaxial compressive strength. The procedure of its determination and the range of compressive strength of common rocks are given later under uniaxial strength of rocks used a building stones. Tensile strength. This may be determined directly or indirectly. The direct method would require elaborate means. The indirect method, which is called the Brazilian test, consists of loading a test cylinder diametrically in such a way that the applied load would develop tensile loosening along the diameter plane of the specimen. The loads are gradually increased till the cylinder is fractured. The load P at rupture thus being known. Transfer strength Ts is calculated by using the formula Ts is equal to 2P by pi dl, where D and L are the diameter and length of specimen respectively. Shear strength. For determining this strength, a bar-shaped specimen is held under grease and supported at its ends below. The shearing strength is calculated by using the formula P by 2 by A, where P is the load at failure and A is the area of cross section of the specimen under the load. This is base plate. This is uniaxial compressive strength test. This is loading test. This is cylindrical slope sample with a length diameter ratio of 2. These are the arrows. This is uniaxial compressive strength test. Tensile strength test. This is lower plate. This is steel plate. This is test specimen. This is upper plate. This is load. This is tensile strength test. Modulus of elasticity E. The modulus of elasticity of rocks indicates the deformation under loads. Such deformation is recovered when loads are removed. This is determined according to Hooke's law. The value of E is determined according to Hooke's law. We say that in elastic substances, stress is directly proportional to strain. It is expressed by relation S by C E. S by C is equal to E, where S is the stress, E is the strain, and capital E is the modulus of elasticity. This is also called Young's modulus. Laboratory results give only rough value because the value for rock mass with its various planes of weakness is required. The modulus of elasticity is tested for rocks in laboratory by loading test specimen, that is commonly slenders of L by D ratio 2 under uniaxial compression. Note here, this is stress, this is strain. This is quasi-elastic rocks, this is semi-elastic rocks, this is non-elastic rocks. The modulus of elasticity is tested for rocks in laboratory by loading test specimen, that is commonly slenders of L by D ratio 2 under uniaxial compression. In quasi-elastic rocks, in quasi-elastic rocks, the stress-strain relationship is almost a straight line till the point of failure occurs. There are massive, dense, and non-foliated rocks of igneous and metamorphic groups like granites, gabbros, dolerites, basalts, and quartzites. Such rocks have E values ranging from 16 into 10 ratio 5 to 11 into 10 ratio 5 kg per centimeter square. Coarse-grained granites, dolomites, sandstones, etc. come under this group. Value of E ranges from 4 into 10 ratio 5 to 16 into 10 ratio 5 kg per centimeter square. In non-elastic rocks, stress strain relation tend to break into an initial zone, too steep slope followed by a curve or the test slope. They are porous and coarse-grained. Their E value is less than 4 into 10 ratio 5 kg per centimeter square of least slope. Laboratory results give only rough values because the value for the rock mass with its various planes of weakness is required. This is usually obtained by seismic shock method mentioned earlier. The modulus of elasticity is tested for rocks in laboratory by loading test specimen, that is commonly slenders of L by D ratio 2 under uniaxial compression.